In this video, I'm going to talk about signed integers, how the computer stores the signed integers. In previous slides, we have talked about the unsigned integers. Unsigned numbers means they are 0 or positive. To store signed integers, computer is going to use a sign bit to represent the negative or positive number. If it's negative, computer use 1 for sign bit. If it's 0, for positive. Okay, let's take a look at storage for 1 byte. 1 byte is 8 bits. The leftmost bit is called a sign bit, and it's called the most significant bit. If it's signed integer, and the computer going to use the leftmost bit to indicate a sign. So if you have a negative number, computer is going to use 1, put in this location. If you have positive number, computer is going to put in the leftmost position. So 1 means negative, 0 means positive. Here we have a note. For any hexadecimal numbers which is greater than 7, and we know that's negative because for 8, that's 1 0 0 0, so that 1 is in the leftmost, so it's negative. For hexadecimal 10 is 1 0 1 0. 1, the beginning is the most significant bit, so it's negative. So this is the rule of sums. Computers have used different ways to represent the negative numbers. Our textbook talks about using tools complement format to represent the negative numbers or store negative numbers in the computer system. This table here tells us the procedures, how to find out a number in tools complement format. For example, this is a negative 1. You want to find out how to write this is a positive 1. You want to find out how to write a negative 1. You follow these procedures. So you want to find out how to write a negative 1, you start with positive 1. And we are using 8 bits for storage. So we have 7 0 then 1. Step 1. You have to reverse your bits. And we reverse the first 7 bits into 1, and the last one reverse into 0. In step 2, you're going to add 1 to the value from step 1. So we copy this down here, and we're going to add 1 to this value. Last step, you're going to sum up. So 0 plus 1 is 1. And the rest just 1, so you copy it down. This is a negative 1. So for any number, you want to find out is corresponding negative part. You start with its positive equivalent. Then you step 1, step 2, then sum up. That will give you negative 2's complement representation for that number. Here I handwrite another example. I use a big number. Suppose we want to convert the negative 315 in decimal into two's complement format for the computer to store. We are going to use this procedure. We're going to find out the start value for positive 315 first. I wrote a few steps here to help you to understand how to get the positive 315 in binary. We have covered this in previous videos. If you forget, here I can give you a quick review. To find out the 315 in binary format, so you divide 315 by 2. So here, this is my shortcut. 315 divided by 2, you get a quotient 157. So you copy your quotient to here. You have remainder 1, so you copy to here. After you have your first quotient, you continue divide 157 by 2. So divide 157 by 2, you got a quotient 78. So you copy to here, and you got the remainder 1. You put it down here. Continue with 77, and you divide by 2, and you get the quotient 39. See, this is quotient 39. Your remainder is 0. So you follow the same logic, and you divide 39 by 2, 19. Oh, here I have a typo. This should be 19 divided by 2. Then 9 divided by 2, 4 divided by 2. Make sure every step you copy the quotient and you copy the remainder. The remainder can be 1 or 0. If it's like a even number, of course the remainder is 0. If it's odd number, the remainder is 1. So when you get a quotient 1, you divide by 2, you don't have quotient anymore, so you have quotient 0, you have remainder 1. And when you reach this step, you have a quotient 0 and a remainder 1, and this is your last step. So your final value will be from 1 all the way up to the top. Remember, you have to copy up. And this is the leftmost digit. Okay, continue with the next slide. So I copied the 315th binary format over here. 1 0 0 1 1 1 0 1 1 from last slide. This is 9 digits, 9 bits. We mentioned in previous slide. Computer only use byte, 2 bytes, 4 bytes, or 8 bytes as storage size. So 1 byte is 8 bits. We have 9 bits, so the storage size cannot be a byte. So we have to go by 2 bytes. 2 bytes is a word. So I copied 7 zeros to the front. Because I have 9 digits here, I need another 7 zeros to meet the 16 bits requirement as the storage size. So after you find out your positive 315, you can follow this table, step 1 to sum, to find out the negative 315. Okay. So my step 1 is to reverse the original 315 in binary. So I made a 7 1 here, and 1 become 0, 2 0 become 2 1, 3 0 here, 1 and 2 0 here. Step 2 is to add 1 to this number. So I add 1 to this. You add each 2 pairs here, and you find the values 1 1 1 1 1 1 1 0 1 1 0 0 1 0 1. So this is a 2's complement format for negative 315. This is negative because my most significant digit is 1. 1 means negative. So this is my answer. Negative 315 in decimal equals this in binary in 2's complement format. If you check YouTube videos I post in the learning resource folder, you will find out some that are talking about the one's complement format for negative numbers. Anyway, we follow their book. This is the book way to have negative numbers in binary. Okay, here I have another case study. Suppose in your test or in your homework, you were given a signed number in two's complement format. Can you convert this back to find out how much it is in decimal? And this is the example. I have 11010011. It's a signed number. To find out this is how much, I have to follow the same procedure here. Okay. 3 steps. This is the leftmost bit is the most significant bit. This is 1, so I know my number is negative. I want to find out how much is the value in decimal or the magnitude for this negative number. I'm going to follow the 3 steps. Copy my original value from here to here. Then step 1, I'm going to reverse my bits. So 2 1 become 2 zeros, then 1 0 1 1 0 0. Step 2, add 1 to step 1. So I copy this value down here, then add 1 to it. Then add each 2 pairs. So this is my final value. How much this is? Let me see. This is 1 to the 1 times 2 to the 5th power, because the index here is 5. This is a base 2. Binary number is a base 2 system, so you have to times 2 to the 5th power. And then I have 0 here, I don't care. And this one, I have 1 times 2 to the 3rd power. Because this is index 0, index 1, index 2, index 3. Then I have 1 here, 1 times 2 to the 2nd power. Index here is 2. Then this one, I don't care, is 0. This one is 1. So 1 times 2 to the 0th power. 2 to the 0th power is 1. So finally, add up all these values, I got 45. So my number is negative 45 in decimal for this given signed numbers in two's complement format. Okay, so even you are given negative decimal number, you can follow this procedure to find out is equivalent to the complement format in a computer. Or if you are given a signed number into the complement format, you can follow the same procedure to reverse back to find out how much is equivalent in decimal number system. How to subtract 2 binary numbers? When you do A minus B, you can say A plus negative B, and we have learned this in algebra. A minus B can be A plus negative B in algebra. Computer has a adding unit. Computer don't use a subtract unit. So when you subtract 2 binary numbers, computer use 2's complement format to add. Actually, there's no subtraction behind. Let's give you the idea here. So if you want A minus B, and we don't want to do A minus B, we want to do add. We we are going to say A plus negative B. So A is the same. We are going to change B to negative format, and this is if you have, this is what, 4, this is 4 plus 8, this is 12, so this is 12 minus 3. We want the 12 minus 3, actually we can say 12 plus negative 3. So in order to say minus, we're going to add. We're going to change this 3 to be 2's complement of 3. So you have A minus B, we're going to change it to A plus negative B. So 12 minus 3, we are going to say 12 plus negative 3. So this is 3 in 2's complement format. 12 minus 3, your answer should be 9. So let's take a look. We're going to say 12 plus negative 3, and let's add. This is 1, this is 2, 2 means 1, 0. And this is 2 plus 1 here, this is 3, so this is 1, 1, and 1, 1, 1, 1, 1, 1, 1, 1. So finally, this should be 9. This is 1 plus 8, this is 9, that's right. So 12 minus 3 can be done, say, 12 plus negative 3. The answer is 9. And it's read in binary format. Ranges of signed numbers. If you have a byte has A bits, you have to use the most significant bit for sign. Let's go back to the previous slide. So if you use this for your sign bit, you can only use 7 bits for negative magnitude. So the range of signed number is going to be smaller in range if you want to store in a byte. The largest positive number you can put into a byte use 7 bits is 127. The smallest number you can put into a byte using 7 bits is negative 128. Negative 128 corresponds to negative 2 to the 7th power. 127 corresponds to 2 to the 7th power minus 1. So if you have a signed word, you want to find out the range, you can use 2 to the 15th power is negative, and 2 to the 15th power minus 1 for the positive, the highest number. A word is 16 bits, and you have to use the leftmost significant bit for sign. So you only can use leftover 15 bits for value. So that's why the range is this much, and it's base 2 and the 15th power and 215 power minus 1. So you can check, verify this. They have the same logic. If you have a double word, you have 32 bits, you use 1 bit for sign, and you can only use 31 bits for value. So this is the smallest number, and this is the largest number you can store into a double word on the 32 bits long. Thank you for watching.